Hey guys, so recently we went over the different kind of atomic theories and stuff like that. And one of the last ones we talked about was the Bohr-Rutherford model of the atom. So today we're going to be drawing Bohr-Rutherford diagrams, which essentially illustrate this theory that we're going to be using to describe the structure and the behaviors of the first 20 elements of the periodic table. Okay, so like I said, these are Bohr-Rutherford diagrams, and they are going to be used to illustrate the Bohr-Rutherford atomic theory, essentially. So you do need to understand how electrons are organized within the different orbits or orbitals. You need to be able to draw Bohr-Rutherford diagrams. You also need to be able to identify different patterns that exist within the periodic table. And then also know how that affects reactivity of elements on the periodic table. Okay, so a Bohr-Rutherford diagram is most important for its depiction of where electrons are. It does also show the number of protons and electrons in the nucleus. Just a reminder, in order to draw these Bohr-Rutherford diagrams, you will have to be able to determine how many protons, neutrons, and electrons the atom has. So the protons is just the atomic number of the nucleus. The number of neutrons is the mass minus the atomic number. And then the electrons are equal to the number of protons, so equal to the atomic number, as long as the atom is neutral. And we'll talk about non-neutral atoms later on. As Bohr described, electrons are located in orbits or orbitals, which surround the nucleus of the atom. The first orbital, which is the one closest to the nucleus, can only hold 2 electrons. The second and third orbitals can hold up to 8 each. Electrons will always fill the closest orbitals first, and then when that closer one is full, they will move outwards from there. So step one of drawing a Bohr-Rutherford diagram is to just draw a circle to represent the nucleus, and then write the number of protons and neutrons inside. Again, the protons is just the atomic number, the neutrons is the atomic number minus the atomic mass, or the mass number. Then we draw dotted lines to represent the orbitals, so those circle around the nucleus. If you don't like drawing dotted lines, you can also use lines as long, like solid lines, as long as those are a different color than the nucleus. And then the fourth step is to just add electrons. Again, starting with the closest orbital and moving outwards. There are 4 different possible locations in that orbital that the electrons can be found: top, bottom, side, or side, as you can see in the diagram up here, top, bottom, side, or side. You don't see them in like these like middle spots here. And electrons do not pair up until all 4 of those spots are filled, then they will pair up. Okay, so that's just what that's talking about. So what we're going to be doing here is you guys are going to go through essentially the first 20 elements of the periodic table and draw Bohr-Rutherford diagrams for each of them. I will get you started here with a couple different example Bohr-Rutherford diagrams, and then you should be able to fill out the rest from there. Okay, so for our first example here, I am going to draw the Bohr-Rutherford diagram for sodium, which is Na. Now, if you look at sodium on the periodic table, it's right here. So it has an atomic number of 11, which means it has 11 protons. That also means it has 11 electrons. And then the neutrons are going to be the mass, which we're going to round up to 23, minus the 11. So if we do 23 minus 11, you get 12. So we will have 12 neutrons. And so from there, I'm going to start by drawing my nucleus. And then on the inside, I write my protons and my neutrons. Now, if you just do this for a couple, that's fine. It's going to start getting a little crammed on some of the higher numbered elements if you draw a big nucleus. So draw your nucleus for a couple like this, but the most important part of these Bohr-Rutherford diagrams is actually the electrons in their orbitals. So for the next one, I'll show you kind of like a shortcut that you can do. Okay, so then I start drawing in my orbitals. And the first orbital holds 2 electrons. One goes at the top and one goes at the bottom. Then I have to move to my next orbital, which can hold up to 8. And I need to get up to 11. So I've got 1, 2, 3, 4, 5, 6. I have to spread them out into those 4 positions before I start to pair any of them up. Now, I still need more. I'm only at 6. I need to get to 11. So I will have to start pairing up electrons now. So I'll go 7, 8, 9, 10. Now that orbital is full. It has 8 electrons. So I will need to draw another orbital. Right now I'm at 10. Again, I need to get to 11. So I put 1 more electron in. So that's what the Bohr-Rutherford diagram for sodium should look like. Okay, for the next one, let's try oxygen. Oxygen, which is right here on the periodic table, has 8 electrons and 8 protons. So protons are 8, electrons are 8. Its mass would be 16, and so 16 minus 8 is also 8 neutrons. Now, in order to save space, again, just because you're doing a lot of these, if you want to just draw the nucleus like that, that's fine. Like I said, the electrons are the most important part of this. On a test or quiz, though, if you're asked to draw a Bohr-Rutherford diagram, you do need to actually write the protons and neutrons. So this is just a shortcut that you can use for some of the examples here, but do make sure you know how to do it this way and practice a couple like this, because that is what I will expect on a test or quiz if you're asked to draw a Bohr-Rutherford diagram. But anyway, shortcut, we just draw in our nucleus. Again, the first orbital can only hold 1, 2 electrons. So then we move to the next orbital. So that's 1, 2, 3, 4, 5, 6. I need 2 more, so I have to start pairing them up. 7, 8. Okay, so that is what this kind of simplified Bohr-Rutherford diagram would look like. Okay, so these are the patterns that you should have noticed when you drew the Bohr-Rutherford diagrams for the first 20 elements. As you move down a group, the number of orbitals increases. And in each group, all the elements have the same number of electrons in their outermost orbit. The electrons that are in this outermost orbit are called the valence electrons, and valence electrons are super important. Valence electrons are probably the most important part of an atom in terms of bonding and stuff like that and how molecules form. So make sure you know what a valence electron is. That'll become very important. So all the elements of the groups have the same number of valence electrons. Single electrons, so electrons that are not in a pair, are the easiest to lose and gain. This is what makes groups 1 and 17 so reactive. Also, the further away an electron is from the nucleus, the easier it is to lose. So elements that have more orbits are more reactive because they can lose electrons more easily. As you move down one group, each element will have one more orbital than the previous one. So that is why reactivity increases as you go down. Okay, so what that all means is, so we did the first 20 elements. So any element in group 1 here will all have one valence electron. And any element in group 2 will have 2 valence electrons. And then if we skip over to here, any element in this group will have 3 valence electrons. This group will have 4, this group will have 5, this group will have 6, this group will have 7, and the last group will have 8 valence electrons. And then as you move down a group, so this top row here that contains hydrogen and helium, that has just one orbital. Anything in this second row will have 2 orbitals. Anything in the third row will have 3 orbitals. These guys have 4 orbitals. So as you move down a group, the number of orbitals goes from 1 to 2 to 3 to 4. But again, they all have the same number of valence electrons, so electrons in that outermost orbital. Okay, the octet rule says elements are most stable when they have full orbits. A full first orbit would just have 2 electrons, and then for the second and third orbits, a full orbit would have 8 electrons. The noble gases, which are the 18th or the last group on the periodic table, are the only ones that all of their orbits are full, which is why they're so stable and so unreactive, because they meet the octet rule. They don't want to change their number of electrons, which is what happens during reactions. Okay, that is it for today's lesson. Please let me know if you have any questions.